Hey Calc 2 kids, welcome to section 7.6, integration using tables. There are gazillions of integral tables, both in text form and on the internet. If you Google integration tables, it will take you to lots of links to websites where you will see thousands and thousands of different tables for integrals. For the sake of this class, we're going to use the table that's attached, or it's in the reference section of your textbook, which I also attached at the end of these notes, and I put it in the handout section of your Blackboard. Keep in mind, this table is limited. There are only about 100 integration templates on it, but there are literally thousands and thousands and thousands of them out there, all right? So when I refer to a specific number entry in a table, I'm referring to the table in the reference section of your textbook, the Stewart textbook. Often when we use tables for integrals, we have to manipulate the integrand algebraically or use some sort of substitution to get it to match a table entry. Also, you are allowed to use the table only when prompted to do so. So on tests, if you're asked to integrate and show all your work, then you may not use the table entry. You'll have to show all the details in between. You can use the table to check your work, but we want to still be able to integrate using all the techniques that we have been studying in Chapter 5 and Chapter 7. All right, so that being said, let's try our first table integral. I said find the integral of the square root of x squared minus 9 all over 2x using tables. All right, so using tables, what we're going to do is we're going to scan through our tables of integrals, and it's not a bad idea. They're sort of broken down into groups. We have forms involving a constant squared plus u squared. U is assumed to be the variable in most tables. We have a constant squared minus the variable squared. Well, here we have the variable squared minus a constant. That brings us to the next section. So you're going to flip through your tables, and you're going to see that this looks a lot like number 41. Right? So 41 says the integral of the square root of u squared minus a squared all over u is, and then here gives me the template. So I'm actually going to write this down. So first note, this 2 is going to causes a little bit of a problem, but we'll deal with that in a minute. So we're going to use number 41 in this case. So half of the battle is trying to identify which one to use. So number 41 says that if you have the antiderivative of the variable u squared minus a squared all over the variable u, and you integrate with respect to u. So you may ask, how do you know what is the variable, u or a? Well, that's where that notation du comes in. It's saying u is the variable and all other letters are understood to be constants. So if you integrate something of this form, the template, the answer is going to be, if you do it correctly using other methods, u squared minus a squared minus, let's see if I can squeeze this all in, the constant a times the inverse cosine of a over the absolute value of u plus c. All right, so here we're going to have to get this to look like this. So let's see, what are we going to need to do? Let me grab my pink pen. All right, so we're going to just replace the x with the u. So we're going to let u equal x, and then a squared is 9, so a is going to be 3. So what do we do about this guy right here? Well, don't forget that's just a constant, and we can pull a constant out. So my integral is really, I have the square root of x squared minus 9 all over 2x dx. I'm going to bring that 2 out front, but a 2 in the denominator is equivalent to 1/2 out front of the integral. So x squared minus 9 all over x dx. Now things line up nicely. We just have x squared. We have 3 squared here, and we have just the variable of integration there. So now we're going to stick in everywhere we see u in the template. We're going to put x. Everywhere we see a, we're going to put 3. So it's going to be the square root of x squared minus a squared, which is 9, or 3 squared, minus a, 3, inverse cosine of the constant 3 all over the absolute value of x plus c. There we go. That's it. So in previous sections, we did trig substitution. So this problem would lend itself nicely to trig substitution. So to do, right? When I ask you to do something, it's highly suggested that you do it. You may see it again. All right, so I challenge you to do the same problem using trig substitution and see if you get the same result. Okay? All right, let's try another one. Let's find the integral of x squared over 9 plus 4x squared dx using tables. So my variable is x, I have a radical, and I have a sum. And, you know, notice that 9 is a perfect square number. And here we have something squared too. So if I flip through my tables, let's see what number this is going to be. I want to look for something like this. I'm going to take my time and I'm going to flip through my tables. Now I'm looking, I have a radical with a sum. So when I look in the very, starting at number 21, notice we have a squared plus variable squared. So that's very similar to this. As a matter of fact, I think it looks a lot like number 26 because we have x squared, we have a squared, and we have plus u squared, which could be our x squared, and then here's my template. So let me write down number 26 here. So I'm thinking I'm going to use number 26. Right, and you may think, well, we have a little bit of a problem with this 4 here because in number 26, it's just u squared, but we're going to do something clever. So number 26 says we have u squared all over the square root of a constant squared plus u squared du. If we can get it into this form, then the result is just going to be u over 2 times the square root of a squared plus u squared. Right, I'm just being really super careful that my eyeballs don't wander and I write down the wrong one. And I jump templates, natural log. So a squared over 2, natural log of u plus the square root of a squared plus u squared. I think I got it all in there. Then don't forget our plus our constant. All right, so you may be a little concerned, and you should be, because we don't just have x squared here, we have 4x squared. So what I'm going to do is keep in mind 4x squared is equivalent to 2x squared. Right? Isn't that true? So how about I let u, watch this clever substitution, let u equal 2x, right? Then we have a couple things going on here. Then u squared is going to be 4x squared. And then don't forget this is really super important. Du is going to be 2 dx. All right? So in other words, 1/2 du is going to be dx. So now let me rewrite my integral. We're going to stick in everything where it belongs. I have x squared all over square root of 9 plus 4x squared dx. So I'm going to get rid of all my x's and replace them with the u's. So x squared is, well, be careful. We know what 4x squared is. So if 4x squared is equal to u squared, isn't it true that 1/4 u squared is what I'm going to replace for x squared? So I'm going to call x squared 1/4 u squared. Dx is, oh, sorry about that. Somebody's alarm's going off. Dx is going to get replaced with 1/2 du. And now 4x squared is going to just be u squared. Right? And then a is going to be 3. Phew. All right, so now let's rewrite this integral. I'm integrating 1/4 u squared all over the square root of, I'll just write this as 3 squared plus u squared times 1/2 du. Now it looks almost like this, except for this 1/4 and this 1/2, but I can pull that out. 1/4 and 1/2 out front is equivalent to 1/8. And now it looks just like the template. 3 squared plus u squared du. I can stick it right in here, right? So now I put everything, I got this. It's going to be, let's see if I can write it all down. So I integrate that, I'm going to get 1/8 times u over 2, the square root, well, a, that's going to be 9 plus u squared, minus a squared, which is 9 over 2, the natural log of u plus the square root of 9 plus u squared plus c. So now we got to put it back in terms of x, so therefore my original integral, x squared, all over the square root of 9 plus 4x squared dx is going to be, so remember u is equal to 2x, right? U squared is going to be 4x squared. So it's going to be 1/8 u, which is 2x all over 2, 9 plus u squared, which is 4x squared, minus 9/2 natural log of u, which is 2x plus the square root of 9 plus 4x squared plus c. And I'm going to get rid of this here, the 1/8. I'm going to distribute it through. Those 2's cancel nicely. We're going to get x over 8 times the square root of 9 plus 4x squared. So again, you have to use some clever substitution. In this, I distribute that 1/8. We're going to get minus 9 over 16, the natural log of 2x plus the square root of 9 plus 4x squared, and then don't forget your plus c. Woo! These take practice and patience. All right. All right, let's go to another one. Let's find the integral of 3x times the inverse sine of 5x dx using tables. So I'm going to flip through. I need to find my trig functions, my inverse trig functions in particular. And I'm going to keep going. I'm going to go all the way to my last page. And if you look at the last page, number 90 has one that looks very similar to this. All right, so I'm going to write down number 90, and then we'll go with this and see what happens. Now, it's not exactly the same, but we can make clever substitutions. I have u, the variable, times the inverse sine of u. Right, du is equal to 2u squared minus 1 all over 4 times the inverse sine of u plus u square root of 1 minus u squared all over 4 plus c. So my guess is this is an integration by parts problem. But it's telling us we can use tables, so that's kind of cool. All right, so what we have here is, let's look what we have. We have 3x inverse sine of 5x. So we don't have u inside the inverse side, we have 5x, but we can just assign that to u, right? So I'm gonna let this be u. All right, so we're gonna let u equal 5x. And don't forget that if you use substitution, you have to let du equals 5 dx. So dx is going to be, well, we'll bring that 5 over here and make it 1/5 on the left. 1/5 du equals dx. So this is going to get replaced with 1/5 du. All right. Now here we have 3 times x, but I'm going to ignore that 3 for a minute, and I'm just going to assign x a value. Well, if u equals 5x, 1/5 u equals x. So this is going to become 1/5 u. So let's put this all together. We're going to integrate instead 3 times 1/5 u times the inverse sine of u times 1/5 du. Now it almost looks like the template. We just have this 3, this 1/5, and this 1/5. We're going to bring those, they're all factors, so we'll bring that constant out front. So 3 times 1/5 times 1/5 is equivalent to 3 over 25 out front. Now we have it in perfect form. U inverse sine of u du. Right. So now we're going to use this template. This will be 3/25 times 2u squared minus 1 all over 4 inverse sine of u plus, I'm going to put this down here so I don't run out of room. U times 1 minus u squared all over 4 plus c. All right, now we got to put it, oh, sorry. I was running a little low there. All right, now we got to put it back in terms of x. So therefore, my original integral, 3x, inverse sine of 5x dx is going to be, let me put this here, right? We have u equal to 5x, so we need u here, we need u squared here. U squared will be 25x squared, and I think that's all we need. So we will have 3/25 times 2 u squareds, so that will be 50x squareds, minus 1 all over 4, times the inverse sine of 5x, plus u, which is 5x, times the square root of 1 minus 25x squared, all over 4, right? Sorry, I lost my train of thought for a minute, plus the constant. Now let's distribute that through. Let me just make sure I did that right. Hold on, 2 times, hold on, let me just double check this. Make sure that I didn't lose a parenthesis somewhere after all this. This was number 92 u squared minus 1 all over 4 times the inverse sine. Nope, that looks good. Right, so now we're just going to get rid of these guys. We're going to distribute this 3 through that. I'm going to call this 150 x squared minus 3 all over 100 times the inverse sine of 5x. That times that is going to be plus 3 times 25, so that will be 15x all over 1 minus 25x squared all over 100. Now 3/25 times c is still just plus c, because remember, c represents any constant in the world. So an arbitrary constant times a constant is still an arbitrary constant. I know that sometimes students don't like that, but that's just how it is, because it says we can add any constant on the end. So adding any constant on the end is equivalent to adding any constant times 3/25. So the last thing I'm going to do here is these 15 and 100 share a common factor. Be careful, we can't cancel these out because we have this 3 up here. So there's this 150 is part of a term. So it's going to be 150x squared minus 3 all over 100 inverse sine of 5x plus, and then we're going to cancel out that common factor, and we'll have 3x square root of 1 minus 25x squared all over, I took out a factor of 5, so it's going to be 20 plus c. Let's do one more. Let's do x e to the 2x squared cosine x squared using tables. Again, you're allowed to use tables if the problem says to use tables. Otherwise, the expectation is you're going to come up with the method on your own. So I'm going to go through and I'm going to look for e's and cosines. You might know it's in the back here. And if you look at number 99, I have e's and cosines, but I don't have x squareds. But if you think about it, if u is x squared, then I would have x squared both inside the cosine and in the power of e. So let's look at number 99 for this guy. Number 99 says if you integrate e to the au cosine bu du, we have a template for this. It is e to the au a squared plus b squared, right? A cosine bu, this is our template, number 99, plus b sine bu plus c. So looking at this, this looks a lot like our integration by parts problems when we ran into those loops. So you could do this by parts. All right, so what do we have? My problem is xe, and I have this x here, but bear with me. 2x squared cosine of x squared dx. So why don't we let's see, inside the cosine, why don't we let bu equal x squared? But you know what? I'm just going to let u equal x squared because that's just a constant. And then du equals 2x dx. Oh, look, x dx. Well, x dx is just 1/2 du. So I'm going to replace this x dx with 1/2 du. And then right here, I have 2u. So this is equivalent to integrating e to the 2u cosine of just u, 1/2 du, which is equal to, I'm going to bring this constant out front, 1/2 e to the 2u cosine u du. Now that looks just like that template. So so the 1/2 is just going to go along for the ride, so e to the 2u, so a is equal to 2. Here we have just the cosine of u, so b is equal to 1. So now we can use this template and stick it all in. Right. So if I stick this all into that template, I get that 1/2, don't lose that guy, 1/2 e to the au, which will be 2u, all over a squared plus b squared, well, a squared plus b squared, which is 4 plus 1, times a, which is 2 cosine of 1u, plus 1 sine of 1u, plus c. So now we got to go back to our u's. We said let u, right? U is equal to x squared. So therefore, our problem, 2x dx, oh yeah, no, that's right, our problem, x e to the 2x squared cosine of x squared dx is equal to 1/2 times e to the 2u, which is 2x squared, all over 5, times 2 cosine x squared plus the sine of x squared plus c. Now let's get rid of that 1/2. Right, and I'm going to distribute. This is going to be e to the 2x squared all over 10 times 2 cosine x squared plus the sine of x squared. And then we never leave 1/2 times the constant. We're just going to call it our arbitrary constant. All right, again, practice. Good luck. The table is attached to the end of the note packet. It's also in your handout. So that's the table that we're going to use on your test. That's the table you can use in your homework. All right, have fun, guys.